Hello students, we're starting the chapter on rotation. I'm going to start by talking about rotational position. So if we have the xy axis, right, y is up and down, x is that way, and you've got something that can rotate, we say that it's at position 0 where this post-it note is right now. So when it's off to the right on the x-axis, right? Imagine that the x-axis is going through the hub and the y-axis is going here. This is position 0. If it's turned this much, we say it's at 90 degrees. We could say that it's at 1/4 of a revolution. Here it's gone 180 degrees. That's half of a revolution. And all the way around, okay, now it's gone 360 degrees, or a full revolution. Let's bring it back to 0. Okay. Now if we went the other way, right, this would be negative 90 degrees. It's hiding behind the fork here, but anyway, that's negative 90 degrees, or negative 1/4 revolution. Okay, so that's nothing new. But because we are doing physics, we need to respect Mother Nature. And Mother Nature doesn't like revolutions. She doesn't like degrees. She wants radians. So what's a radian? Okay, so what we have to do is say, okay, we're going to measure off the radius of this wheel. Notice the word radian, radius, right? There's something in common there already. So, okay, so we've got here that the radius of this wheel is 32 centimeters. Okay, now we make this piece of paper go round and round and round and round and round until it's gone from the beginning point an arc distance of 32 centimeters. That means it's gone 1 radian. So 1 radian, the definition of a radian is the angle that takes it around an arc distance equal to a radius. So now, okay, so I'm just checking my notes over here. I've got my notes. So 1 radian turns out to be about 57 degrees. So this would be about 45, and here we have 57. All right, and then, all right, so now if we've gone twice that radial distance, an arc distance of twice that much, okay, so that's 2 radians, which do the math, 114 degrees. Okay, now of course if we go the other way, now we've gone a negative 1 radian, negative 2 radians, and so on. Yeah, so 1 revolution, right, if you do the math, the circumference of a circle is 2 pi times the radius. And so that means that if I go a full turn, 1 revolution, that would be 2 pi radians. Now, of course, if I go, starting again, I get at 0, if I go the other way, this would be negative 2 pi radians. Okay. All right, students, let's talk about positive and negative rotation. I've already alluded to the idea that this would be positive rotation and this would be negative rotation. But there's a thing called the right-hand rule, which you're going to need to get familiar with. Right? What I need you to do right now, I know this feels stupid, but bring up your right hand. Okay? And now, I'm going to do something with my right hand. I'm going to make it go, let's see, which way? This thing is turning this way. So that means I want my fingers to curl the same way that the wheel is turning. So you see, if the wheel is going this way, I want my fingers to also go this way. All right? And now, here's the thing. My thumb, or your thumb, which way is it pointing? Right? If your fingers are curling this way, then your thumb, my thumb, is pointing towards you, right? Now, so that means that your thumb is pointing towards you when you have a positive rotation. Now, what if I go the other way, right? To make my fingers curl the other way, now my thumb is pointing away, like this, right? So my fingers go like this, the thumb is pointing away. All right, now it turns out that physicists use a rotation vector. So if the wheel is pointing this way, the rotation vector is pointing towards you, like my thumb. If the wheel is pointing the other way, the rotation vector is pointing away from you. Now, a vector that is going to go right to you. Think of a arrow, right? An arrow. And it's about to hit me in the eye. What's the last thing I'm going to see? It's the tip of the arrow. So an arrow, a vector that's coming towards you, is represented by a dot. Now, oftentimes we'll put a circle around the dot to kind of make it more clear, but a dot means an arrow, a vector that's pointing towards you. Now, what if you're shooting the arrow and it's going away from you? When you see the arrow going away from you, you're going to see the feathers of the arrow, and usually the feathers are set up in a cross configuration. And so a vector that's pointing away from you is going to be represented by an X, a cross. And usually we put in a circle around it to make it slightly more clear. Okay. So that means that a rotation vector like this, that rotation vector it's on the axis of rotation, and it points towards you, and it's going to be a dot. And if it's going the other way, it's going to be an X, right? So this would be an X, and this would be a dot. Okay, so I'm back at my regular spot, and let's take a look at the notes here. So I've already talked in my outdoor demo about how the radian is defined. And here, this is 1 radian, this is 2 radians, this is 3 radians. And the distance from here to here, that distance is equal to the distance from the middle out to the rim. Let's say this is a bicycle wheel. So from the hub to the wheel and from here to here are equal distances. And so when that happens, and this is an angle of 1 radian. And here we have that a radian is 180 degrees divided by pi. That's a good conversion factor. And pi being an irrational number, we have that 1 radian is 57.2957, and then there's an infinite number of digits after that. Okay, let's see. Let's move on to what else we need to talk about. Okay, a full revolution is 360 degrees. 360 degrees is 2 pi radians. And the reason why we go with radians is that Mother Nature prefers radians. And another reason is that the math is going to be easier in radians. Notice the little detail here. I have a counterclockwise rotation, and there's a dot. And here I have a clockwise rotation, and there's a cross. The dot represents the rotation vector coming towards us, and the cross represents a rotation vector going away from us. And so the way to remember this is to use the right-hand rule. I'm looking at the screen right there. I see the rotation going like this, and there's my thumb, and whatever my thumb does, that determines which way the rotation vector is pointing. Okay, we discussed this, a dot. Yeah, okay, we already talked about all of this. This is how you put your thumb. This is supposed to be a hand, not a very good drawing, I'm sorry. And okay. Okay, let's demonstrate a constant positive angular velocity. So right now it's rotating in the positive direction, and the rate of increase of position is linear. So that's a constant, positive constant rotational velocity. Let's make a constant negative, right? So now omega, the rotational velocity, is negative. Okay, so now let's talk about angular velocity. So regular linear velocity got the letter v, but rotational velocity or angular velocity, the two words are used interchangeably, angular, rotational. Anyway, the symbol is omega. This is not a W. This is the Greek letter omega. When I write it, I write it like this, like that. That's a lowercase omega. Now you probably have seen the uppercase, the capital omega, which looks like that. But for angular velocity, we're using lowercase omega. All right, so let's define it. First, let's talk about angular position. Let's say that your wheel has rotated to here, and so this right here is our initial angular position, and then it keeps going, and it ends up here. This is our final angular position or rotational position, and the change in position is the final minus the initial. And we define that the average angular velocity is the change in angular position divided by time. And the units are going to be radians per second. So the angle is going to be in units of radians. Not always, but usually when we're doing physics problems, especially if we're doing physics problems that involve rotational energy, rotational momentum, those physical things are Mother Nature kind of things, and Mother Nature wants radians. Now, sometimes in engineering and so on, like you might have revolutions per minute, like cars, the engine of a car, revolutions per minute, and so on. So it's not like it's always radians per second, but in this physics class, it's going to be mostly radians per second. Okay, now here comes something really quite confusing and surprising. When you read a scientific journal, you're going to see things like, okay, the thing was rotating at so many 1 seconds. Well, you see, the thing is that the unit of radians is not really a solid unit. It's not like a kilogram where you can feel what a kilogram is. It's not like a meter. You know what a meter is. Radians are really a ratio. It's a ratio of the arc distance over the distance from the middle to the edge. And so, okay, a distance might be in meters, and then this other distance might also be in meters. Meters divided by meters, oh, that's nothing. And so radians are kind of, in a weird way, kind of nothing units. And I call them phantom units right here, okay? Now, this is not an official thing. This is just a Halverson thing, all right? But that's the way I sometimes, talk about it. And so when you're doing homework problems and you have radians just like disappearing, don't panic. It's okay. And so yeah, this is what I just said. Okay. Coming back to positive and negative. If something is rotating counterclockwise, we say that's a positive rotational velocity, and it gets the dot for the vector pointing towards you. And if it's going clockwise, we call that a negative rotational velocity. And it gets the X, which represents the feathers of the vector arrow going away from us. Now, let's talk about angular acceleration. It gets the Greek letter alpha,
right? This looks kind of like the fish, but no, this is the lowercase alpha in the Greek alphabet. I mean, it kind of makes sense, right? Regular acceleration was the letter A, the first letter in our alphabet. And then here we have the first letter in the Greek alphabet, lowercase alpha. Anyway, average angular acceleration is defined to be the change in velocity over the change in time. Right? So it's just like before, just like with linear velocity. Acceleration, average acceleration was the change in velocity divided by the change in time. All right. Now, the units are going to be radians per second squared. Remember, when we did linear acceleration, the units are meters per second squared. But now it's radians per second squared. And for the reasons I just mentioned, radians are phantom units, so to speak, quote unquote phantom units. And so oftentimes in a book or a scientific journal, you're just going to see 1 over seconds squared. And then to make things even more confusing, I mean, not on purpose, but anyway, 1 over second squared can also be written seconds to the -2. And you're going to see that if you get into scientific journals. And they're doing that just to save money or to save space. It takes less space than writing 1 over second squared. Okay.
Let's do an increasing rotational velocity. So we're going to have an acceleration. So that's alpha. So right now, the velocity is 0, omega is 0, the acceleration is 0. Now let's start making this thing speed up. Okay, so it's going faster, 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 faster. So as long as I can make it accelerate, we have an alpha. Okay, I can't go any faster than that. Now the acceleration is 0. It's going at a constant rate, positive. Okay. Let's give it a negative acceleration. So the omega is negative, it's more negative, it's more. So we have a negative acceleration until finally I can't go any faster. So now the constant negative velocity. That was fun. Yeah, let's stop this thing now. Ouch, 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 ouch. There.
Let's compare now linear and rotational quantities. So for position, when we were doing chapter 4, our position had the symbol x and the units were meters. Now we're doing rotations and the symbol is theta for how much we've rotated, and the units are radians. Usually radians, okay? Sometimes it might be revolutions, sometimes it might be degrees, but for the most part, it's going to be radians. Velocity, it gets the symbol v. It has units meters per second. But now that we're doing rotation, our rotational velocity or angular velocity is omega, has units of radians per second, or you might see 1 over seconds. And acceleration, symbol a, units meters per second squared. That's for linear acceleration. Now we're doing rotational acceleration. The symbol is alpha, and the units are radians per second squared, or you might just see 1 over seconds squared. Okay. Okay, well, we're almost done with this first video. Let's finish up by talking about the big 5. All right, now you guys know about this, and you know the big 5 for linear motion, and we have the equivalent corresponding big 5 for angular motion or angular kinematics or rotational kinematics. There's so many different ways to say it. So here is the first of the big 5. the acceleration is missing from this one. And so we have that the final position, angular position, is equal to the initial position plus 1/2 the initial velocity plus the final velocity. Now, if you take this whole thing, that's the average velocity times time. The second one is, now in the second one, the initial position, final position are missing. And this one is simple. It says that the final velocity is equal to the initial velocity plus the acceleration times the time. Here is the third one. The velocity is missing. So the final position is equal to the initial position plus the initial velocity times time plus 1/2 alpha t squared. And there's many problems where this is 0 and this is 0, and so you just have theta equals 1/2 alpha t squared. And that's the third one. And the fourth one, now the fourth one and the third one are like really similar. The difference is that in the third one, the final velocity is missing, whereas in the fourth one, it's the initial velocity is missing. And so, okay, maybe I'm not going to spell it all out, but you know what is happening here. And then finally, here's the fifth one. You have the final velocity squared equal to the initial velocity squared plus twice the acceleration times the change in angular position. And this one has the time missing. Okay, now, right here I'm seeing something pretty important. I do need you to open the book and look at these examples. Example 10-1, example 10-2, and active example 10-1. And here are the page numbers. All right, I think this is a good place to stop. Work hard. Bye-bye.